Section 2.4, Iterative Optimization-Based Learning. Linear models, coupled with quadratic loss, as was in equation 212, are gifted with a closed-form solution for the parameter estimates, as appearing in equation 216. That equation was an equation with a pseudo-inverse. This solution, which is based on the pseudo-inverse, that was in 217, is well studied in the field of numerical linear algebra and is typically suited for efficient numerical evaluation, a topic that we do not cover here further. For example, in the section above, the pseudo-inverse computation of the 60,000 by 785 design matrix X used for MNIST digit classification using the one versus all method can be evaluated in about a second on a modern laptop. Nevertheless, there are multiple scenarios where this closed-form solution may not be used. This is a case when we use alternative loss function to the quadratic loss, such as 218 or 219. Those were the absolute value loss and the Hubbard loss. Problems with using the explicit optimal quadratic solution may also arise when the number of features P is very large. In such cases and others, more generic methods for optimization are needed. We now present a general iterative optimization method for obtaining this solution. It can be used in such scenarios where the pseudo-inverse based computation does not work, yet more importantly, it serves to illustrate how gradient-based optimization interplays with machine learning. Indeed, the more complex deep learning models on which this book focuses use this type of method, and its generalization almost exclusively. We note that there are other methods used as well, and Chapter 4 focuses entirely on optimization. Our purpose here is simply to introduce the essence of the most basic technique, namely gradient descent. So here we see algorithm 2.1, gradient descent. As input, we have a data set, we have the objective function, and we have an initial parameter vector. The output is an optimal theta. We start in step 1 with theta getting the initial parameter. And then we repeat steps 2 to 6, where at each time in step 3 we compute the gradient of the objective function with respect to theta. We determine the learning rate alpha if we need to determine such a learning rate alpha. And most importantly is step 5, where we update theta to be theta minus the learning rate multiplied by the gradient. And we do this until theta satisfies some termination condition. It's both theta and c of theta that satisfy the termination condition and return theta. The gradient descent procedure presented in algorithm 2.1 executes over iterations indexed by t012. So t is the iteration index, and works by taking small steps in the direction opposite the gradient. That is, it reverses downhill each time, trying to descend in the steepest direction. In its simplest form, steps are determined by a fixed alpha greater than 0, called the learning rate. After some initialization with the initial vector theta 0 equals theta init, in each iteration t, the next vector theta t plus 1 is obtained via theta t plus 1 is theta t minus the learning rate alpha multiplied by the gradient evaluated at theta t. The algorithm repeats 220, where the key object that requires computation at each iteration t is the gradient of the cost function, gradient of c at theta t. For complex deep learning models, this computation is one of the core components of a deep learning framework, and is carried out using the backpropagation algorithm studied in Chapter 5. However, for simpler models, such as the linear model or logistic regression type models of Chapter 3, we have explicit expressions for the gradient. In the case of a linear model with quadratic loss, we have already computed the gradient in equation 214. And we can represent it as the gradient of the loss at a point theta is 2 times x transposed, open bracket, x theta minus y, where x is your design matrix and y is your vector of features. So this is an explicit expression for the gradient that we have for linear models and we typically don't have. In general, the algorithm iterates over t until theta t plus 1 and theta t, so two theta evaluations in two different time steps, are close to each other, as measured by some stopping criteria, such as we have here in equation 2.22. For example, the norm of their difference is less than some epsilon, with some fixed epsilon greater than 0. Other stopping criteria and variants of this method are studied in detail in Chapter 4. The final theta t plus 1 is used at theta hat, so that's our estimate of the parameters. And if alpha and epsilon are well chosen, the algorithm output may closely approximate the optimal theta. One of the main difficulties with the application of gradient descent is choosing the learning rate alpha. As an illustration, figure 2.7 presents a contour plot of the squared error loss function associated with simple linear regression, similar in nature to the Boston house pricing data example of figure 2.3a, where we optimize to find theta hat, which is beta 0 hat and beta 1 hat. We could have also called this B and W, where W is only one-dimensional. When running with epsilon equals 10 to the minus 5 and starting theta init at the origin, so that's at the point 0, 0, we see that if the learning rate alpha is 0.01, the algorithm terminates near the optimal parameters in about 3,100 iterations. If alpha is bigger at 0.0235, the algorithm terminates near the optimal parameters quicker, with about 1,450 parameters, iterations. It follows a more jagged path. We'll see that in a second. Finally, when running with a learning rate that is slightly higher, say 0.024, the algorithm diverges and does not terminate at all. The plot in this divergent case is only for the first 300 operations, the 300 iterations, where growing oscillations are still in the vicinity of the optimum. With further iterations, the values converge, the value quickly diverges. So let's look at this figure. So what we have in this figure, first of all, observe that we're optimizing here over a parameter space that's only of d equals 2. So that's simple linear regression. In this case, our contour plot can be plotted, and what you see is the contours, and this here is the actual minimum point of this contour surface. Okay, now we start at the origin, that's a point 0, 0, that's here and here. Okay, so that's where we start. That's theta init. And we can run gradient descent using different values of the parameter vector. Different values of the learning rate. So if we run it with the learning rate, which is 1/100ths, so that's this red line, okay, that's alpha 0.01, we follow such a path and reach the optimum. Now, if we actually get a higher learning rate, then we actually get to the optimum quicker, even though at first what we see are these blue oscillations. But if we get a bit too greedy and increase the learning rate even more to 0.024, then what we get are these oscillations such that diverge. So the point here is that learning rate is a tricky hyperparameter. Of course, it's illustrated for this very simple case of simple linear regression. The simple example illustrates that the value of the learning rate alpha is crucial. Different values implied drastically different behaviors. A more thorough investigation of gradient descent and its generalizations is in Chapter 4. Interestingly, for linear models, more explicit results are available as we present now. So the results that we present now are specific for linear models. Learning rate analysis for linear models. In general, there's not a simple analytical way to determine a suitable learning rate alpha. Chapter 4 presents adaptive generalizations of gradient descent, and Chapter 8 presents some heuristics for choosing alpha. Yet, universally, there are no closed-form recipes. Nevertheless, when it comes to the special case of the linear model, analysis of the dynamics of gradient descent is analytically attractive, and we may explicitly describe the range of alpha for which convergence takes place. This description is not necessarily of direct practical use, however, it gives insight into the nature of gradient descent. So let's do this. Consider the linear model with design matrix X, that was given in equation 210, and denote lambda max as a maximal eigenvalue of the Gram matrix X transposed X. So remember, the Gram matrix is a square matrix, it's a D by D matrix. Okay, for example, for the example we saw above, it's 2 by 2 because D is 2. But in general, it's D by D. And lambda max is its maximal eigenvalue. We can show that gradient descent converges to the solution of the normal equations 215. So we're going to reach a solution as long as the learning rate alpha is not greater than O(n) over the maximal eigenvalue. So this is like your maximal learning rate that you could choose. And a footnote about, oops, jumped here, hold on. A footnote about convergence. Here's a footnote. Here, convergence formally means that for any epsilon 2, there is an epsilon of 222 where the algorithm terminates in a finite number of iterations where theta star minus theta t plus 1 is less than epsilon 2. So if you want to get as close to epsilon 2, you can actually set some epsilon in the algorithm. These epsilons should be rounded epsilons, okay, in the algorithm, and that implies that you converge. Okay, that's just it's a bit of a formal definition to what we mean by the algorithm converging. It's not so important. Note that for data used in figure 2.7, lambda max is about 20,700, okay? And n is 490. So, all right, so this is the data here. N is 490. We have 490 observations. So the X matrix is 490 by 2, and X transposed X is 2 by 2, all right? And the maximal eigenvalue of this 2 by 2 matrix is 20,670. Okay. Now, keep in mind that this here is a symmetric matrix, and hence eigenvalues are real, and then you can actually speak about the maximal eigenvalue. You don't need to speak about the absolute value of it or something like that. Sorry, jumped here again. And then in 490. Hence, in this case, the algorithm converges for alpha in the range of, now if you do 490 divided by 20,000, you are going to get 0 by 20,000. If you do 490 divided by lambda max, 20,670.33, you're going to get this upper bound 0.02371. And this bound is in agreement with the examples of figure 2.7, where the first two paths have alpha in this range, 0 to 0.2371. And the third path is just a bit above because we got alpha is equal to 0.024 and we diverge. Okay, keep in mind that in the second path, we took alpha 0.0235, and 0.0235 is less than this maximal learning rate that would yield convergence. Okay, so first of all, we're just saying, hey, we actually can find an upper bound on the learning rate. Again, this type of thing is just for illustration, because in terms of practical deep learning, because we can only do it for the linear model, really. We're not able to do this for other models. To see 2.23, so let's get now a proof of 2.23, use a gradient expression 2.21. So we have the gradient expression here, 2.21. So we can take this gradient expression and stick it inside here. That's what we're going to do. And the gradient up to the rule of 220 to obtain the recursion. So theta t plus 1 is actually theta t minus the learning rate times the gradient evaluated at theta t. And we can rearrange this as an affine expression, theta t plus 1 in theta t, where we have a matrix A and a vector C. Okay. So the gradient descent for linear systems, because the gradient in itself has this nice expression, is an affine dynamical system. Or in short, theta t plus 1 equals A times theta t plus C. Such a recursion is known as an affine discrete time linear dynamical system, and equilibrium points of such system denoted theta star satisfy, well, when you, an equilibrium point, you'd want to have this equation to hold. That's what theta star. Or if you multiply I by an identity and rearrange, I minus A times theta star equals C. In our case, using the matrix A and the vector C, it's evident that such equilibrium points are solutions of the normal equations. So the normal equations, of course, solve equilibrium points or describe the equilibrium points. We'll only have a single equilibrium point if X is full rank. And for simplicity, let's assume here that X is full rank, and hence there is a unique theta star. It follows from linear system theory that the spectral radius of the matrix A, so A is a square matrix, okay, A was this square matrix, okay, because the Gram matrix is a square matrix, and A is a square matrix, and we'll just remind you what the spectral radius is in a second, determines the convergence or non-convergence of the iterates theta t to theta star. Specifically, if the spectral radius of the matrix A is less than unity, then theta star converges to theta star, theta t converges to theta star for any initial solution. And if the spectral radius is greater than unity, then for any initial theta 0, the sequence diverges. So in the border case, if the spectral radius happen to be exactly 1, is indeterminate. Hence, putting aside the border case spectral radius of 1, we see that convergence occurs if and only if the eigenvalues of A are within this. Now, the spectral radius of the square matrix, just to remember, is the largest magnitude of the eigenvalues. In case a matrix is real, we may say it's a magnitude of the largest eigenvalue. So here we actually meant in case the matrix is symmetric and the eigenvalues are real. Okay, so that's a bit of a mistake here. Not a big deal. So we have this matrix A here, and it's all about, hey, we would want its spectral radius to be within -1, 1 for this system of gradient descent to converge. Now, since X transpose X is a symmetric matrix, the eigenvalues of X transpose X are real. And since X transpose X is positive semi-definite, that's a property of any Gram matrix that one can show, the eigenvalues are actually positive. So they lie, or non-negative, and they lie in the range 0 to lambda max, with lambda max greater or equal than 0. Further, the eigenvalues of this guy lie in the range. So now if you just multiply X transpose X by a constant here, it's a scalar value, they lie in this range. And if you add that to the identity, they lie in this range. So when you do an identity plus a constant times a matrix, you affect the eigenvalues. Thus, the critical inequality that ensures that the spectral radius of A is less than 1 is that this thing holds. And now we can rearrange and represent it in terms of alpha, And that gives us this very nice 2.23. Now, again, it's very nice, but it's not so important and useful. It's more illustrative. It's just so you can see that in a nice linear model, you can actually describe when things converge and not, depending on the learning rate. And you can actually see the dynamic range of the learning rate that is okay. But in general, you can't. More advanced models. The loss landscape and standardization of inputs. In section 2.1, we present standardization of inputs via 2.2. So that was a while back already, but what we did there in 2.1 is we basically subtracted the mean and divided by the standard deviation, okay? Where sample mean and sample standard variances are computed via equation 2.1. We now show that such standardization also affects the loss landscape, so often yielding improvement in the execution of gradient descent. As above, our analysis is in the realm of linear models, where explicit analysis is possible. To illustrate the concept, we consider a simple case of linear model with two input features, x1, x2. So now take this linear model where you have two input features, but you actually don't have an intercept. You have two parameters, beta 1, beta 2. We could have also called them w1 and w2. This is simple. This is similar to the simple linear regression model of section 2.2, yet without an intercept term beta 0. Here with n data samples, the n by 2 design matrix X has column composed of the vectors xi1, that's the first vector, and that's the second column vector for I equals 1, 2. The labels of the vector y are here. And the model parameters are theta, beta 1, beta 2. The square loss cost function, where for simplicity we omit the one on n term, is as follows. So here's again the square loss cost function. A contour plot for some arbitrary non-standardized data is illustrated in figure 2.8a. So this is a contour plot of the loss. Okay, so this would be your beta 0 and beta 1. Yeah, and beta 0 and beta 1. It's evident that the contours of the cost function are ellipsoids. They're generally ellipsoids, so that's what you get when you get this kind of quadratic loss. For some given cost level C, it can be shown that the length of the principal axis of the ellipse, we can actually represent the length of the principal axis of the ellipse. There's a square root of k over lambda I, for I equals 1, 2, where lambda 1, lambda 2 are actually the eigenvalues of the Gram matrix, and k is the contour level minus y transpose y. Okay, so that requires some work to show, but it can be shown. With this, the elongation of the ellipses, which is the ratio of the length, is this thing. Okay, so the bigger this ratio Rx is, the more elliptical the whole thing is. So that's the ratio of the square root of the ratio of the eigenvalues. Now, when standardizing the inputs, each of the columns of X is transformed separately via what we had in equation 2.2. So in each column, we subtract the mean and divide by the standard deviation. In such a case, the loss function associated with the standardized data is C theta given Z and Y, the standardized things. Standardized design matrix, say, where we denote by Z the design matrix of the standardized data. It can now be shown that Z transposed Z is actually this nice matrix. It's n times matrix that has 1 on the diagonals, where rho is the sample correlation between the two features. Okay. And from Cauchy-Schwarz and just sample correlations, we know that rho lies between -1 and 1. With such a standardization, an explicit form for the Gram matrix Z transpose Z, we can compute the eigenvalues of Z transpose Z to be lambda 1 is 1 plus rho and lambda 2 is 1 minus rho. And thus the elongation of the ellipsoid has this form. It is evident that in cases where the correlation between the features is low, then RZ, you actually have very little elongation. And this implies that the loss landscape of the standardized data is much more similar to figure 2.8b. So here, this is what you'd get if RZ was 1. Okay, perfect RAM contours. Now, in terms of gradient descent, taking steps in the loss function, such as figure 2.8b in the perfectly round case, is generally more efficient than using the loss landscape in figure 2.8a. Hence, it's expected that as long as rho, the correlation coefficient, is not too close to 1 or -1, carrying out standardization will help gradient descent converge faster. Note that while this analysis is carried out for the simplistic P equals 2, D equals 2 linear model with quadratic loss, the principle often applies to more complicated loss landscapes as well. Further note that with standardization of the features or any other transformation, one also has to encode the standardization transformation as part of the deployed model, since the model is now for the standardized features Z instead of X. So after you use the model, you have to unstandardize it to get back the results that you want for predictions. But anyway, this little subsection just gave a bit of insight into how standardization can also help optimization, because here the left-hand side is in a sense hard for optimization, while the right-hand side is easy for optimization. And that concludes our section 2.4. As always, we hope that you enjoyed this video. Let us know what you think in the comments below. Thank you.